Hello, class. I wanted to discuss the solutions to a few of the key problems on the test number one review, since we may not get to go over all of these things in class before the test coming up on Thursday, March the 4th. Of course, you can ask questions of Madison in her SI sessions, or you can also book an appointment in Math Center, an online appointment with Math Center, right? And you can also ask them questions about the review sheet or any other questions you need to ask to prepare for test number one. Or of course, you can find me in my office hours, right? And ask me questions directly as well. So we're not going to go through the whole review, but again, just a few of the key questions from the review, starting with this lengthy number one question. This doesn't really, the questions in this particular problem don't really require a lot of computation. They're really more conceptual questions. And so you don't want to miss easy points on this problem number one. And if you understand about tangent lines and instantaneous rates of change and derivatives and function notation, then you can get all of the points for this question really easily and quickly. Okay, so let's look at some of these. So you're told, right, that here we have a function g that's graphed, that's this curve here that you can see, right? And there are several points, 5 points here that are plotted on the graph of this curve. And along with each point, there's a line drawn adjacent to the curve at that particular point, right? And all we want to determine first is it possible that that line that's drawn at the given point, is that possibly a tangent line to the graph? Does that look like it could be a tangent line? Remember, a tangent line is going to coincide or is going to duplicate the graph close to a given point, right? Right, so let's look here. First, let's look at point A. Here's the line that's drawn right there, right at point A. And again, what you want to ask yourself is, if you were to zoom in at point A, you just have to imagine this, right? But if you were to zoom in close to point A, would the line and the curve coincide? Would the line duplicate the curve, or vice versa? Would the curve duplicate the line? If we zoomed in very, very close to this point A, on the curve, right? Obviously, here far away from the point A along this line, the line is not going to duplicate the curve, right? But the question is very, very close, arbitrarily close to point A. Does the line duplicate the curve? And my answer is yes, I think it does, right? I think this does look like a tangent line to the curve at the point A. I think if we zoom in on this point, the line and the curve would coincide, right? Same thing for point B, okay? So if you can barely see this line that's drawn here at point B. It's this line right here that has this positive slope, okay? And in fact, the answer here is so clear, right? Because already you cannot, close to B, right? You can't even distinguish the line from the curve, right? They certainly overlap each other close to this point. So closely, right, that I can't even see which is the curve and which is the line. So indeed, close to point B, the line and the curve do coincide, right? They duplicate one another. So I would say again, yes, it looks like this line could be, maybe it's not, but it certainly looks like it could be the tangent line to the curve at the point B. All right, on the other hand, if you look at point C, where you've got this vertical line drawn through the point C, see clearly that cannot be a tangent line, right? There's no way that close to this point, this vertical line and this curve are going to look the same, right? In fact, close to this point C, I think this curve, since this is a turning point on the curve, right? I think close to this point C, this curve is going to appear to be a flat line, a horizontal line, as you zoom in really close to this point C. But here, the line that's drawn is a vertical line. Well, horizontal lines certainly don't duplicate vertical lines, right? And so I would say, yeah, this is way far off, right? This line drawn at C could not be is not the tangent line to the curve at this point C. What about D? Well, I think again, yeah, that looks like a pretty good tangent line to me, right? Okay, again, close to the point D, I think the curve and the line coincide, right? They duplicate one another close to the point D, right? Not way over here on the left or way over here on the right, but close to the point D. See the line and the curve are very close. They're very similar to one another. So yes, I think at D we have drawn what appears to be a good tangent line. Now at point E, not a tangent line, right? Okay, if you zoom in on here close to point E, this line and this curve just don't resemble each other, right? Okay, this line has a lot more slope in it than the curve does at point E. At point E, the curve is sort of flattening out, right? Okay, but this line that's drawn has a very clear negative slope, right? So I would say no, that line drawn at point E, not a very accurate tangent line at all, okay? So those are why we have the answers that we're given. All right, now let's see if we can answer these questions. We're going to have to scroll around a little bit because we do have to refer back to this function g, okay? And this is where you need to be aware of a function notation, right? So you're just given this inequality stated, and you just want to say, could that be true or is that false, okay? And so here we have g prime, not g, but g prime of -2 greater than 0. Is that true? All right, so let's look at -2. There's -2 on the x-axis, right? Okay, and so that indeed corresponds to that point A. And what we want to know is, what about g prime of -2? Now look, if the prime is not there, right, you would just have g of -2. G of -2 just means the y value that corresponds to an x value of -2 on this curve. That would be something like 2.5, right? Okay, very close to 2.5. So g of just g without the prime of -2 would be something like 2.5. And well, that is a positive number. So the answer here would be true if the prime is missing. But what about g prime of -2? What's the difference between g of -2 and g prime of -2? G prime of -2 means the rate of change, the instantaneous rate of change of the function g at -2, okay? Or remember, the other way we state this is the derivative of the function g at -2. Derivative and instantaneous rate of change, those are interchangeable terms, okay? So what this refers to, of course, is not the y value that matches the x value of -2, but at -2, what is the slope of the curve, okay? Is the curve increasing or is the curve decreasing at the input -2, all right? So if you look here, well, there's the input -2, and indeed, you can see that the curve is increasing here, right, at the input -2. So the slope of the curve is indeed positive, all right, right? The slope of the curve is positive, or the instantaneous rate of change, or the derivative of the curve here at -2, or the function g at -2 is positive. So again, this answer is true. Now, we can really see this very clearly in this particular instance, right? Because the tangent line is drawn here. Remember, the g prime of -2, the way you compute that value, right? Not just guessing if it's positive or negative, but the way you actually calculate it is by finding the slope of the tangent line to the curve at the input -2. Well, we already mentioned, right, that here at the point A, which corresponds to -2 on the x-axis, right? Here at the point A, we have the tangent line drawn. Clearly, that tangent line has positive slope. It's because it's going uphill from left to right. So we know that g prime of -2 has to be positive, right? The rate of change, the instantaneous rate of change, the slope of the curve, the derivative of the function g, those are all sort of interchangeable terms. all of those are positive, right? Okay. So that means greater than 0. So our statement here is true. All right, what about g prime of 1? All right, so g prime of 1. Well, let's look. There's 1 on the x-axis. Ooh, that corresponds to the point B. We had a tangent line drawn at the point B also, right? There's that tangent line. That tangent line has positive slope because this function is increasing at the point B, right? Okay, and so that means g prime of 1 also is going to be positive, all right? Because the function is increasing at 1, the tangent line has positive slope at 1, the slope of the curve is positive at 1. All of those the statements are all just the same way of saying the same thing, okay? All right, what about g prime of 2? All right, so what's the instantaneous rate of change, or what's the slope of the curve at 2? Well, here at 2, that was the point C, right? That is a turning point. So if you think about what the tangent line is going to look like at a turning point here, it's going to be a flat line. So remember, this is not the tangent line. A tangent line here would be a flat line, but flat lines have slope 0. So at this turning point, the curve has slope 0. But 0 is not positive, right? It's close to being a positive, but it's not quite positive. So this is a little bit of a trick question. G prime of 2 is not greater than 0. It's actually equal to 0. It appears in the picture that it's equal to 0. So this is false. What about G prime of 5? Is that where our next point is located? Yeah, there's 5 on the x-axis. There's so that corresponds to the point D, right? But the slope of the curve here at D is negative because the tangent line has a negative slope, right? The tangent line is falling. Likewise, the curve is falling right at the point D. So the slope of the curve at the point D, same as the slope of the tangent line, is negative. So the answer here is false. This cannot be greater than 0. In fact, this derivative is less than 0. What about g prime of 8? Is that a trick question, or is that, no, that corresponds to the point E, right? So g prime of 8, well, here, this is not the tangent line. So we really cannot use this line to help us answer the question because this is not an appropriate tangent line. But we can still answer the question without drawing the tangent line accurately because we can see that although it's not increasing, not decreasing very rapidly, the function is decreasing here. It's still going down at the point E. And if the function is decreasing at the point E, that means its slope is negative. When you draw the tangent line is going to have negative slope. So the answer to the next part there still is false. G prime of 8 cannot be greater than 0. It's actually got to be less than 0. All right, so there's the review there of question number 1. All right, let's get down now a little bit. We're going to go down quite a bit, and let's go down to question number 7. Kind of, in a way, a similar question, all right, because it also deals with slope of this curve and a tangent line. So here's this parabola here is the graph of a function named f. All right, so that's this U-shaped curve here, right? And we apparently on this function is the point 4 and -2. So I've written in the coordinates for this particular point, and drawn right there at that point on the curve is a tangent line. So here's the tangent line to this function at the point 4, -2. See, close to this point, right? If you zoom in very, very close to this point, the tangent line and the curve would coincide. You couldn't really distinguish the two, right? And so we're going to use that tangent line to help us answer questions about the rate of change, the instantaneous rate of change, or the derivative, same terminology, right, of this function named f. Okay. Now, the first question, though, is not about instantaneous rate of change. This is about net change. So that's our more primitive method, right? One of our more primitive methods of measuring change in the outputs of a function. All right, so we're asked here to compute the net change in the function f from x equal minus 2 to x equal 0, right? So that's just asking us how much of the y value, how much do the y values change when we move from x equal minus 2 to x equal 0? That's what net change means. That's got an easy formula to calculate, right? You calculate f of the second input, x equals 0, minus f of the first input, x equals minus 2. So you compute this as f of 0 minus f of minus 2. And let's see, can we find those two things on the graph? Let's see, f of 0, there's 0 on the x-axis, so f of 0 would be minus 2. That's what I have written in there. And what about f of minus 2? Oh, did yeah, what about f of minus 2? There's minus 2. So f of minus 2 is up here at 4. So f of minus 2 is 4. You're subtracting, right? This minus sign and this minus sign are the same. So you have negative 2 minus positive 4 because f of minus 2 is positive, and you get negative 6. See, that makes perfect sense, right? As you move from minus 2 on the x-axis to 0 on the x-axis, right? As we move from minus 2 on the x-axis to 0 on the x-axis, notice the outputs from this function fall from 4 down to negative 2. So that means there's a net change of negative 6, right? The outputs fall by 6, okay? All right, now, so this is the formula for computing net change in a function. What about percent change between these same two values? Well, percent change has an easy formula also. You simply take the net change, which we already calculated in the first part here. The net change is minus 6, and you divide that by your first output value, right? The output value that corresponds to x equal minus 2. And then you convert that to a percentage by multiplying by 100%. So you have minus 6, that's the net change, divided by 4, because that was the y value that matched x equal minus 2, right? So you divide by 4 and then multiply by 100%, you get minus 150%. So in percentage terms, this net change of minus 6 is, in percentage terms, that would be minus 150%. So quite a big drop, right, in the outputs as we move from, in the y values, right, as we move from x equal minus 2 to x equal 0. Now, let's find the slope of this tangent line that's shown here on the graph, right? Okay, so so we have this tangent line drawn here at the curve at 4 and minus 2, and we want to compute its slope. So a tangent line is just a line. So of course you calculate its slope by using the slope formula for a straight line, right? And to use that slope formula, you need to have 2 points on the line. Well, 1 point on the line is pretty obvious, right? That's 4 and minus 2, because that's also the point that's on this parabola. And then we simply have to pick off another point on the line. So we're not given another point on the line, so we're going to have to estimate another point on the line. Let's see what point I used here as another point on this line. It looks like I used the point 8, 6, right? Let's see, is that a point on the line? 8, 6. There's 8, and yeah, here on the line, right, yeah, at 8 on the line, the matching y value indeed appears to be 6. So here's a second point on the line up here at 8 and 6. And so now we just use our slope formula, right? So we take 6 minus a minus 2. That's in the numerator, right? So that's the change in the y values, change in the y coordinates, divided by the change in the x coordinates. That's just 8 minus 4, which is 4. So we get 6 minus a minus 2, that's 6 plus 2 is 8, divided by 4 is 2. So the slope of the tangent line is, that's shown there in the graph, is 2. What about the equation for that tangent line? That's very easy to write down in point slope form. So if you have the slope of a line like we do, we have the slope of this tangent line is 2, right? And you have a point on the line. We actually have 2 points on this tangent line, so we can use either one of them. then it's very easy to write down the equation for the line. You just take y equals the slope times x minus the x coordinate of the point that you know that's on the line. So the x coordinate of our point, I'm going to use this point, 4 minus 2. We could have used this point, but I'm going to use this point. So we have 2 times x minus 4, that x coordinate of this point, and then just add on the y coordinate of the point outside of the parentheses here. Well, y coordinate of this point is minus 2. So I'm just going to put in here minus 2. Okay, so there's the equation for that tangent line that's shown, this line right here. All right, now these other two questions are very easy. You just have to remember that the slope of the tangent line is the same as the instantaneous rate of change. So the instantaneous rate of change of f at the input 4 is the slope of the tangent line. We just computed the slope of the tangent line to be 2, so that means this instantaneous rate of change is also 2. And then f prime of 4, well, when you use the prime notation, when you use the prime symbol, right, in function notation, right, that means instantaneous rate of change of the function. But we just calculated the instantaneous rate of change of the function at the input 4. That is 2. So this value I just calculated is 2. I just get to fill it in back here, right? So part E and part F here are really asking the same thing, right? Okay. Here it's just spelled out in words. Here it's written in function notation. But the meaning of instantaneous rate of change and f prime of 4 are the same. By the way, this is, remember, also instantaneous rate of change, also called the derivative. So if I ask for the derivative of the function f at the input 4, you would also say 2. Okay. All right, now let's try also here question 8. So this is just a really very similar question. It's just asked in context. So you have to sort of interpret the values that you get here in the context of the problem. See, this problem 7, there's no context in this problem. You just have the graph of the function and this tangent line, right? Okay, but in problem 8, you're given a little bit of a story here to go along with this graph. What this graph shows, so this is the function called p, and this function p shows the population of some sort of pest or some sort of insect, probably, on an acre of land where we're doing an experiment with a pesticide. So we're trying to determine the effectiveness of some pesticide applied to a portion of land, in this case, an acre of land. So we're doing that by spraying the pesticide on it, then actually counting the number of pests that are on the, so these probably are insects, right? The number of insects that are on the on that acre of land, you know, a given number of months after we apply the pesticide. Okay, so you can see sort of what's happening to that population. It's decreasing at first, right after we apply the pesticide, right? So that's killing the insects. And then at some point, the pesticide begins to wear off, and so the insect population starts rising again. Okay. First, now let's see. It says, what's the domain of this function? Well, that's not really a calculus question, right? Okay, the domain of this function starts at 0 here on the, in this case, the m-axis, right? The same as the x-axis, right? The horizontal axis here. So the graph begins at 0. The domain begins at 0 also because we have a closed dot here. So that means that the graph does not extend to the left, right? That wouldn't make any sense because m here is time in months, and you're not going to have a negative amount of elapsed time, right? So so the domain begins at 0, and in this case, it cuts off at 8 because this graph is cut off at 8 with this closed dot. Okay, so we're just supposed to understand, because the closed dot is here, that the graph doesn't continue to the right. So the domain here is from 0 to 8 along the horizontal axis. Now, another easy question, not really a calculus question. It says, interpret P of 0 in the context of the problem, right? So what does P of 0 mean? That is function notation. There's no prime there, right? No prime here above the P, no prime mark there. So this is just regular function notation. So what P of 0 would mean is what is the pest population at time 0 when M is 0? Well, when M is 0, that's when we start the experiment, right? That's when the pesticide was going to be sprayed on. So this means an easy way of saying this would be, P of 0 means the initial pest population, the pest population at month 0. So in other words, initially when we start the experiment, P of 0 is the number of pests on that acre of land, number of insects on that acre of land. And if you read that off of the graph, you have to estimate it a little bit, but I estimated that to be about 17.3. So so P of 0 is 17.3, but what that means is the initial pest population. So that's 17.3 thousand. Here's another question, again, not a calculus question. It just says express the following statement in function notation. The pest population 3 months after the pesticide is applied. Notice they don't tell us what that pest population is, but they want us to express this quantity, whatever it is, in function notation, right? So that would be P of 3, right? That's what P of 3 means. It's just a mathematical way of saying this sentence, okay? P of 3, pest population after 3 months, just like P of 0 was the pest population after 0 months, right, at the beginning of the experiment. We don't have to evaluate this. It doesn't say evaluate it, so it doesn't say calculate P of 3. We could, from looking at the graph, right, we could get an estimate for P of 3. It's something above 14, right? But that's not what we're asked for in the problem, so we don't have to put it. Now, here we get to some more calculus type questions. It says, what's the average rate of change? Average rate of change from M equals 0 to M equals 6. So from month 0 to month 6, on average, how much did P change? Okay, all right, so remember the average rate of change calculation is really just a slope calculation, right? It's really the slope of the secant line that connects 2 points on the curve. All right, so what's that formula for average rate of change? It's going to be your function at your second input, right? Minus the function at your first input. So we would do P of 6 minus P of 0. That's really the net change also from month 0 to month 6. But then you divide that by 6 minus 0. You divide that by the change in the inputs, right? So you have P of 6 minus P of 0 divided by 6. Well, we calculated a moment ago, we estimated that P of 0 was 17.3. P of 6 is, I looked at the graph and decided that was 13. Yeah, that looks about right. There's 6, so P of 6, yeah, that looks like 13, right? So you have 13 minus 17.3 divided by 6. That turns out to be, now that should be minus, I left the minus sign off. So I need to correct that. So that's minus 4.3 divided by 6, which is minus 0.72. Okay, so on average from from M equals 0 to M equals 6, the pest population decreased. I did put decreased, but I forgot to put the sign here. The pest population decreases by 0.72 thousand per month, okay? So I'll fix that on the answer key, all right? So again, let's look at the interpretation again. On average, from M equals 0 to, from month 0 to month 6, from M equals 0 to M equals 6, the pest population decreases by 0.72 thousand per, right? All right, now in G, just another average rate of change calculation. So I'm not going to go through this one. Here we want to find the average rate of change from 4 to 8. So you just do this calculation the same way. The average rate of change from 4 to 8 would be P of 8 minus P of 4 over 8 minus 4. So you get 14.5 minus 14. You can estimate these values from looking at the graph. And so that's a P of 8 apparently is close to 14.5. P of 4 is close to 14. So you get 0.5 over 4, which is 0.125. So there's the average rate of change from M equal to M is 8. This is sort of a trick question. It's another average rate of change question, but they want to know, and here we want to know the average rate of change from M equals 5 to M equals 9. So if you try using the average rate of change formula, you'll get P of 9 minus P of 5 over 9 minus 5. But remember, you cannot compute P of 9 because the domain stops at 8. Remember, in our very first question here, we said, oh, the domain here is from 0 to 8. This graph stops at 8. And so that means P of 9 is undefined. So you cannot do this calculation. So the answer here is just undefined. All right, now keep going here. Same question. In part I, it says sketch the tangent line to the graph at the input 5. So here you're going to have to do it by hand. And that's what I have drawn in here. You can see it drawn in. So I drew this in by hand. There's the input 5. And there was my guess for what the tangent line would look like at the input 5. So if you draw this tangent line, you may draw it a little bit steeper or you may draw it a little bit flatter, but you'll come up with something pretty close to the same thing that I drew, right? Okay. You'll look about like this. And then we're going to use that to answer some of the remaining questions. So once we've drawn that tangent line, once we've sketched that tangent line, so answers may vary a little bit, right? Now we want to estimate the slope of that tangent line. And so to estimate the slope of the tangent line, you've got to pick 2 points off of that tangent line. Make sure you pick points on your tangent line. So I picked the point 5 and 13.2. That's this point right here. So that's clearly on the tangent line. The X value is 5. And I estimated the output value as being about 13.2. And then I also used this point, but you could have used other points on the tangent line, whatever is convenient for you. But make sure you pick points off of the tangent line if you're going to compute the slope of the tangent line. So I thought the coordinates for this point would be 7.5 and then 12, not 0, but 12. Look very carefully that y value here is not 0, but it's 12, going from 13 down to 12 along this horizontal line. So 7.5 and 12. Did I do that correctly? Yes. Right. So these are the 2 points that I used, and then I just used the slope formula to calculate the slope of the line, the tangent line that contains those 2 points. I came out minus 0.48. So the slope of that tangent line at the input 5 is minus 0.48. Once you've got the slope of that tangent line, then now you're in good shape, right? Here it says estimate the instantaneous rate of change of the function p at the input 5. That's the same as the slope of the tangent line. Remember, slope of tangent line, instantaneous rate of change, or derivative, those are all the same. So the slope of the tangent line is minus 0.48. So the instantaneous rate of change is minus 0.48. So p prime of 5 also is minus 0.48. Now in M, let's see. Here, we don't have to calculate this instantaneous rate of change or this derivative. It's given to us. So it says, suppose p prime of 7 is 0.7. Interpret this value in the context of the problem. So p prime of 7 is 0.7. What is that telling us? That tells us that at exactly 7 months, the pest population is increasing because this is a positive number, and it's increasing by what amount? Well, by this amount, which is 0.7 thousand per month, because we're measuring our elapsed time in months. So our interpretation is like the interpretation of a slope, okay? Because, well, right, instantaneous rates of change, our derivatives are a type of slope, right? They're slopes of tangent lines. Okay, I'm going to pause here for a moment and then be back in just a second. Okay, so we're back here. Let's look now at another problem 10, which is going to be kind of similar to the previous problem. All right, so this is we're asking some calculus questions here, but again in the context. So this function, this graph models the average amount of social welfare spending. So that's the value that we're calling y. This is going to be measured in thousands of dollars. The average amount per person, and then the input values here along the x-axis are elapsed years after 1970. So a 0 here would be 1975, would be 1975, etc., up to looks like 40 would be 2010. Right, so you can see that that social welfare spending has been increasing, right, but not always at the same rate. Sometimes it's increasing very rapidly, sometimes it's not increasing, right, very rapidly. Okay, so let's look at the first question. It just says, suppose that you are given that f prime of 25, so the rate of change of f, or the derivative of f at the input 25 is 0.38, all right? Let's actually look at the graph again at 25. So here's 25 on the x-axis, and we're told here that the slope of the tangent line, or the slope of the curve at the input 25 is 0.38, okay? Well, that seems like that's a plausible slope right there at the input 25. To estimate that, we would actually have to draw in a tangent line here, right, at the input 25, and then compute the slope of that tangent line, but we're given that that is apparently 0.38. And we just want to interpret this value in the context of the problem, okay? So that's pretty easy to do. We would say in at x equals 25, in other words, in 1995, not from 1 year to a second year, that would be average rate of change. But for instantaneous rate of change, we are referring to a specific input, right? In this case, the input 25, that means a specific year, the year 1995. So in 1995, average social welfare spending on each person was increasing because this number is positive, right? So we know this was increasing by, and then it's 0.38 thousand per year, right? Because our outputs are measured in thousands. And then we have to throw in the per year, right? Because remember, this is a rate of change, okay? So it's not just that social welfare spending was increasing by 0.38 thousand, it was increasing by 0.38 thousand per year. All right, now the second point here is let's estimate the inflection points. So we're actually going to have to look at the graph right now and actually see if we can figure out where those inflection points are. So that's a little bit of a tricky task, and answers may vary here slightly. But as you're looking from left to right, as you're looking from left to right here on the curve, right, you can see that at first the graph is concave down, right? It's concave down, but then this piece is slightly concave up. So you switch from concave down to concave up. That means there's been a change in the concavity, right? And where that change occurs is the inflection point. So I estimated that that inflection point was right about there. I think right there is where it's changing from concave down to concave up. So I just estimated the coordinates of that particular point. So again, answers may vary slightly. I said that was 9 and 4.3. All right, so this part is concave down. This part is concave down, but as you move further to the right, I'm sorry, this part is concave up, right? This part is concave up, but as you move further to the right, you're going to see the graph becomes concave down, right? So this part is concave down, this part is concave up. So again, we have to have a place where that switch occurred. And I'm guessing it's right here, right about there, which is at the input 22 and a half, right? Halfway between 20 and 25. So, so that was my guess for where the second inflection point is, was 22 and a half. And then the output there to me looked like about 6.3. So I think the two inflection points are 9 and 4.3 and 22.5 and 6.3. But when you were estimating your inflection points, you might have gotten values that were a little different. Okay. Now let's look also on this page at question 11B. So this is going to be one of the harder questions for you on this test, or actually on the semester. So we've got a function here named h, and it's got this pretty straightforward formula. It's a quadratic function because we have the input squared. So h there, its formula is x squared minus 3x plus 2. And we want to find the average rate of change from just this arbitrary input x, so this variable input x, to this second input x plus h. So this is an average rate of change from starting at the input x, a variable, going up to the input x plus h. So that would be x plus something a little bit more than that, right? All right, so so let's use our average rate of change formula. So remember, the way the average rate of change formula is just the slope formula, right? So you would take your second, your terminal x value, right? Your second x value, plug it into your function. So you get h of x plus h minus h of x, because that is your starting input. So h of x plus h minus h of x over, and then just the difference in your two x values. So you would have x plus h minus x, and that's going to simplify to just h. The rest of this now is really algebra. You have to calculate x of x plus h, and then you have to calculate h of x. That's pretty easy. Simplify some algebra, and once you're through simplifying, whatever answer you get, which is going to involve some variables, that's it. All right. So how do we compute h of x plus h? Remember, you're just going to take x plus h and plug it into your function formula for x. So you would have x plus h substituted for x here. That would give you x plus h squared, right? See, or you have x squared, you plug in x plus h for x. So you get x plus h squared minus 3 times. Now you just plug in x plus h for x. So you get 3 times x plus h, and then plus the 2. So all of this part is h of x plus h. Minus, because of this minus sign that's in the formula, so minus, and then just plain h of x. Well, here's h of x already. You know what h of x is. That's the first thing we're given in the problem. H of x is x squared minus 3x plus 2. So you're going to subtract off x squared minus 3x plus 2. When you're subtracting that off, this minus sign is the same as this minus sign. So when you subtract that off, because it has multiple terms in it, it's got 3 terms in it, x squared minus 3x plus 2. Make sure you put that in parentheses. Otherwise, you're going to make a sign mistake, and then things are not going to end up nicely at all at the end. So put all of this inside parentheses to subtract it off. All right, now continue with the algebra. So we have to square x plus h. Remember, that means multiply x plus h times itself. So when you take x plus h times x plus h, I didn't write it out, but you get x squared plus 2hx plus h squared. That is x plus h squared. It's not just x squared plus h squared. It's more complicated than that, right? You have to take x plus h and actually multiply it times x plus h. And when you do that, you get x squared plus 2h times x plus h squared. And then, well, this second part is easier. Minus 3 times x plus h, that's minus 3x minus 3h, right? You just distribute the minus 3. So you get minus 3 times x is minus 3x, minus 3 times h is minus 3h. And then don't forget the plus 2, that's still in here. And then just remove the parentheses by distributing the minus sign. So you get minus times x squared, that's minus x squared, minus times minus 3x is plus 3x, and then minus times plus 2 is minus 2. Now, some good things will happen at this point. A bunch of terms are going to cancel. So here you have plus x squared and minus x squared. Those disappear. Here you have minus 3x and plus 3x. Those disappear. Here you have plus 2 and minus 2. Those disappear. So in the end, you end up with just 2hx left plus h squared minus 3h. All the other terms in the numerator cancel. All this divided by h. Well, h divides nicely into all of the terms in the numerator. So you can divide h into 2hx. That will leave you with 2x. You can divide h squared into 8. I'm sorry, you can divide h into h squared. That will leave you with just h. And then you can divide h into minus 3h, which just leaves you with minus 3. There's your final answer. You just get 2x plus h minus 3. See, that simplifies very nicely. When you're doing these average rates of change computations with variables, if you do them right, usually they're going to simplify easily, like this one. Okay, one more. Let's look at one more problem. Problem number 13, which is like problem number 12. So in 13, we're looking at a graph of a function, and we're going to answer some questions about this function. Well, actually, about its derivative. So, so here's the graph of this function f, kind of an unusual shaped graph, right? This kind of V-shaped graph. And first thing we're asked to explain is, why does f prime of 1, why is that undefined? So why is f prime of 1 undefined? Here's 1 on the x-axis. So why is f prime of 1 undefined? Remember, to have a rate of change, an instantaneous rate of change at a particular input, the graph has to be a smooth, unbroken curve at that input. But so part of that restriction is the graph has to be smooth. But right here at 1, the graph is not smooth because you have a sharp corner point here at the input 1. See, this graph comes down to this very sharp point and then goes up again. So that's why f prime of 1 is undefined, because the graph is not smooth here at the input 1. It is unbroken, but it's not smooth. So there's the explanation. So no instantaneous rate of change, no derivative at the input 1. Functions do not have to have instantaneous rates of change at every input. All right, let's keep going here. Express the following value in function notation. It's the same function f, and they want us to write they want us to write down the instantaneous rate of change of f at the input 6. How would we express that in, there it is in words, how would we express that in function notation? Well, instantaneous rate of change, you use the prime notation, right? So you would write f prime of 6, not f of 6. That means the output at the input 6. But if you write f prime of 6, that means the instantaneous rate of change at the input 6. So this is a very easy question. You just write down f prime of 6. So instantaneous rate of change corresponds to prime in the function notation. Keep that in mind. Same graph now, but now what we've done here, same function, but different graphs. Now what we've done is we've zoomed in on certain little pieces of that graph that we saw back on the previous page. So the question is, which one of these four enlarged versions of the function f could be used to estimate the instantaneous rate of change at the input 6? Remember, we just expressed that in function notation in the previous problem. But now if we actually want to calculate that, which one of these graphs would help us actually calculate f prime of 6? Well, remember, to calculate f prime of 6, you're going to have the tangent line, right? So you can compute the slope of the tangent line at the input 6. To get the tangent line, the only way we know so far to find the tangent line is to zoom in on the graph near the input 6 until the function looks like a straight line. That's the only means that we have right now, really. Well, I guess we could try drawing the tangent line by hand. That's a second method. But another method is to zoom in on the graph close to the input 6, right, until the graph looks like a straight line. So which one of these is that correct zoom in? Well, let's see. It's not this one because this doesn't look like a straight line enough, right? I can still see some curvature. This is slightly concave down. So I can still see some curvature in this graph. So I don't think this is correct. Let's see. What about this one? This does look like a straight line. I don't see any curvature here. Unfortunately, notice we didn't zoom in at the input 6. You have to zoom in at the input 6 if you're going to compute f prime of 6. Well, here we're zooming in from 3.4 to 4.6 on the x-axis. Well, that's not going to help us all very much at all, right? It might help us compute the rate of change at 4, right? Or the rate of change at some x value from 3.4 to 4.6, but it's not going to help us to compute f prime of 6. 4 is obviously not the right answer, correct? That's the original graph, so that's not helpful. So the answer here is 2, right? Notice this does look like a straight line now, so we have zoomed in close enough so that the curve looks like a straight line, and we have zoomed in on the input 6. So we could use this graph, this enlarged graph, to help us estimate f prime of 6. All right, so how do we do that? Well, you just pick 2 points off of this quote unquote straight line, right? This really isn't a straight line, but it looks like a straight line, so it's going to behave like a straight line. So you pick 2 points off of this quote unquote straight line, and then just compute the slope between those 2 points. So that's what I did in part D. Let's see, what points did I pick? So I picked 6 and 4. 6 and 4, this point. That's a pretty obvious point to pick. And then I also picked the point 5.4 and 3.75. Did I do that right? Here's 5.4. And does this look like 3.75? Yeah, I think so. So I used that point. Or you could have used any other point or any 2 points that you wanted to off of this straight line. So you could pick completely different points. And then I calculated the slope between these 2 points. So that's all I've done here is calculate the slope between these 2 points. So you take the difference in the y coordinates, right, divide by the difference in the x coordinates, and you end up with about 0.42. So my estimate for the instantaneous rate of change at the input 6, f prime of 6, in other words, is 0.2. Okay. Well, there are some of the key problems from the review. There's lots of other questions on the review, and you should try to do as many of those questions as possible before you take the test, okay? So you've got the solution sheet, even if you don't have explanations, video explanations for all of these answers. You do have the written solutions, okay? All right, so I'm going to stop there. And I'll see you guys in class.